is 203186.
Hi, my name is Nur Aisha binti Hasanuddin. My metric number is 202990.
Hi, my name is Nuri Najwa and my metric number is 202534. When you heard about Big Bang, automatically talk about the expansion of the universe. Now, many discoveries, astronomers and physicists have shown beyond a reasonable doubt that universe in fact had a beginning. The Big Bang theory is an effort to explain what happened during and after that moment. So, how did we come to this conclusion? In 1926, while developing a classification system for galaxies, Edwin Hubble, the inventor of Hubble telescope, discovered an odd fact. Almost every galaxy he observed appeared to be moving away from the Earth. He knew this because the light coming from the galaxies exhibited redshift. Light waves from distant galaxies kept stretched by the expansion of the universe on their way to Earth. Astronomers first assumed that these were Doppler shifts and used a relationship between wavelength of source of light measured now on Earth from a source receding at speed and the wavelength shift measured in the rest frame of the source when it was emitted. We can derive this relationship by inverting Doppler effect, making subscript changes and using wavelength equals to c over f. The result is wavelength of source equals to wavelength shift power of root c plus v over c minus v. Wavelength from receding sources are always shifted longer wavelength. This increase in wavelength is called the redshift. In 1929, they had formulated what became known as Hubble's law. Hubble's law basically states that the greater the distance of a galaxy from ours, the faster it recedes, with the equation expressed as v equals to h naught over r. There is an experiment associated with it. Take a balloon and mark some points on it to represent the galaxies. Now, if we start inflating the balloon, the points marked on the balloon will appear to be moving away from each other as the balloon expands. Similarly, the distance between galaxies is also found to be increasing and thereby the universe is considered expanding. In the beginning, all matter forming the universe existed in one place in the form of a tiny ball that is singular atom with unimaginably small volume, infinite temperature, and infinite density. Well, to be honest, where did it come from? We don't know. Why did it appear? We don't know. This tiny ball then exploded violently. This led to huge expansion. The universe that we know was born. Time, space, and matter all began with the Big Bang. Prior before that, there is nothing. In an expanding universe, gravitational attraction between galaxies should slow the initial expansion. But by how much? Whether the universe continues to expand indefinitely should depend on the average density of matter. If these attractions are strong enough, the universe should expand more and more slowly and eventually stop, then begin to contract, perhaps all the way down to what's been called a big crunch. On the other hand, if gravitational forces are much weaker, they slow the expansion only a little, and the universe should continue to expand forever. We can derive an expression for the critical density needed to just barely stop the expansion. The formula is critical density equals to 3h naught power of 2 over 8 pi g.
So now I will talk about dark energy, dark matter, and the accelerating universe. Astronomers have made extensive study of the average density of matter in the universe. One way to do so is to count the number of galaxies in the patch of the sky. Based on the mass of an average star and the number of stars in the average galaxy, this effort gives an estimate of the average density of the luminous matter in the universe, that is, matter that emits electromagnetic radiation. You are made of luminous matter because you emit infrared radiation as a consequence of your temperature. It is also necessary to take into account other luminous matter within a galaxy, including the tiniest gas and dust between the stars. Another technique is to study the motion of the galaxy within clusters of galaxies. The motion are so slow that we can't actually see galaxies changing position with a cluster. However, observations show that different galaxies within a cluster have somewhat different redshift, which indicates that galaxies within a cluster are moving relative to the center. So, the speed of the motion are related to the gravitational force exerted on each galaxy by the other members of the cluster. By measuring the speed, astronomers can determine the average density of all kinds of matter within the cluster, whether or not the matter emits electromagnetic radiation. Observation using this and other techniques show that the average density of all matter in the universe is 31.5% of the critical density, but average density of luminous matter is only 4.9% of the critical density. In other words, most of the matter in the universe is not luminous. It does not emit electromagnetic radiation of any kind. At present, the nature of the dark matter remains an outstanding mystery. Some proposed candidates of the dark matter are weakly interacting massive particles, which are hypothetically subatomic particles far more massive than those produced in accelerator experiments. So, whatever the true nature of dark matter, it might form halos around galaxies. Whether the true nature of dark matter is by far the dominant form of matter in the universe. For every kilogram of the conventional matter that has been our subject for the most of this chapter. So, including electron, proton, atom, molecules, block or inclined plane, planets and stars, there are about 5 of half kilogram of dark matter.
Nucleosynthesis is the process by which heavier chemical elements are synthesized in the interiors of stars from hydrogen nuclide and other previously synthesized elements. Precisely which elements are involved in nucleosynthesis depends on the age and mass of the star. The most prevalent reaction in smaller stars like our Sun is the fusion of hydrogen into helium by the proton-proton chain. In more massive stars, this fusion occurs via the carbon cycle. When a star is burning hydrogen in its core, it is main sequence star. In older stars such as red giant, nucleosynthesis involves the burning of heavier elements created by earlier fusion. For example, helium may burn via the triple alpha process. More massive stars over 8 solar masses also fuse carbon into neon and magnesium, oxygen into silicon and sulfur, and silicon into iron. The nucleosynthesis of the iron is prescore to the transition of the supernova phase. Our solar system formed about 4.5 billion years ago from a dense cloud of interstellar gas and dust. The cloud collapsed possibly due to the shock wave of a nearby exploding star called a supernova. When this dust cloud collapses, it forms a solar nebula, a spinning swirling disk of material. At the center, gravity pulls more and more material in. Eventually, the pressure in the core was so great that hydrogen atoms began to combine and form helium, releasing a tremendous amount of energy. With that, our Sun was born, and it eventually emits more than 99% of the available matters. Matter farther out in the disk was also clumping together. These clumps smashed into one another, forming larger and larger objects. Some of them grew big enough for their gravity to shape them into spheres, becoming planets, dwarf planets, and large moons. In other cases, planets did not form. The asteroid belt is made of bits and pieces of their early solar system that could never quite come together into a planet. Other smaller leftover pieces become asteroids, comets, meteoroids, and small irregular moons. Therefore, in the standard model of the universe, a Big Bang gave rise to the first fundamental particles. They eventually formed into the lightest atom as the universe expanded and cooled. The cosmic background radiation is a relic of the time when this atom formed. The heavier elements were manufactured much later by the fusion reaction inside the star.